Well, I'm certainly grateful to Katie who invited me to talk today, but most of all I think we're all very impressed with the program she was able to organize. Yeah? Okay, so as you can see, the title of this talk includes a revisited, and this means that this is the third and hopefully final installment of the series of paper on the subject. And this is joint work with Rui. Okay, so throughout the talk, I will denote by F isometric immersion of a Riemannian manifold into Euclidean space. Everything I'm going to say extends immediately to any other space of constant curvature. And let me remind you that given such a submanifold, the scalating space is just the subspace of the Euclidean space, spanned by all tangent and curvature vectors of all smooth curves through the point. Yeah? So if it happened that all scalating space, I mean at all points, yeah, just are parallel to a fixed q-dimensional Euclidean subspace, then the submanifold reduces codimension. Yeah? In other words, it's containing some affine subspace of the dimension, the same dimension. So I say here that it's a natural problem to study. Yeah? What happens if the scalating spaces form a non-constant proper family of subspaces? What do I mean exactly that it's natural? Yeah? Well, of course, if you say consider a surface in Euclidean space in high codimension, high it means more than 5 for a surface. Yeah, you always have, yeah. I mean, you cannot fill out the space, yeah. So you will not conclude any restriction on the geometry of the surface, yeah. So this problem is only natural when you are working in low codimension, yeah. So low codimension means that the codimension of the isometric immersion is low with respect to the dimension of the original manifold. Yeah? And in this case, you expect, yeah, since this situation is not a generic situation, that it must have some consequences of the geometry, yeah, of the manifold and the submanifold also. Yeah? Okay, so in order to make the situation more formal, I recall that the first normal space of the isometric immersion at a point is just the subspace of the normal space spanned by the second fundamental form. Yeah? So in the osculating space I just mentioned is just the orthogonal sum within the tangent space plus the first normal space. Yeah? So the fact that all osculating spaces are parallel to a fixed proper subspace, yeah, means that all those first normal spaces form a proper normal subbundle, yeah, where they have, at least in any subset where they have constant dimension. Yeah. And this subbundle is parallel in the normal connection. I mean, it's parallel in the connection induced from the connection in the Euclidean space to the normal bundle in the submanifold. Yeah? So what we care about here is when this first normal subbundle, yeah, is non-parallel. Let me say that all result I'm going to discuss is of local nature, so there is no restriction assuming that all subspaces which show up have constant dimension, since they happen to have it in some open dense subset of the manifold. Yeah. Okay, so if the first normal subboundary is part of the normal connection, you reduce codimension to the dimension of the to the rank of the subboundary. Yeah. Okay. So I will forget for some time the first normal bundle. I will discuss something which is may even seem unrelated, but it's not. Yeah? Which is ruled extensions. Yeah? Okay. So I start with a isometric immersion. I assume that its normal bundles split orthogonally in two subbundles. Yeah? So this subbundle has dimension, a rank small l, which is not trivial. I mean, it doesn't be 0 or equal to the codimension. Yeah? And also assume that at each point, D, which is the kernel of the projection onto P of the second fundamental form, have constant dimensions, so they form a tangent subboundary, non-trivial one. Yeah? In this situation, I will also assume that P, and hence L, is parallel along D in the normal connection. Yeah? In fact, by the definition of D, this really implies that P is constant in the Euclidean space along D. Okay. So I call E the orthogonal complement, the tangent bundle of E, and I defined a tensor, yeah, which takes a tangent vector in E, a normal vector in P, take the derivative in the Euclidean space, yeah, and then the E plus L component. Yeah. So the image of this tensor at each point is what I call gamma. Yeah, so you easily see there are some bounds, yeah, for the dimension, yeah, of gamma, yeah. And then I define another vector, fine vector bundle, which is just which I call lambda, which is just the orthogonal complement of gamma in E plus L. Yeah. So I call R the rank of gamma, so it turns out to be this number. Well, so fundamental fact, yeah, in this geometric situation. Well, it turns out that D is an integral distribution. Yeah. The other thing is that, that gamma is transversal to the tangent boundary. Yeah. So you can add, yeah, D plus gamma. They are not orthogonal. Yeah. And call this delta. Yeah. So delta is an affine, yeah, bundle over M, which happens to be constant along the leaves of D in the Euclidean space. Okay? So that's fundamental property. Well, now comes the ruled extension. By ruled extension, I mean that at each point of the original submanifold, you add Euclidean subspace, or part of it, yeah, which is going to be the ruling, yeah. So that's the operation, yeah. You add lambda to a point on the image of F, and this, of course, you want this capital F to be an immersion, so you have to eventually restrict yourself to a tubular neighborhood, yeah, of the zero section of the affine bundle, yeah. So that's what I do, yeah. So you can say that capital F extends small f, yeah? Yeah. One is just the other composed with inclusion. And of course, when you pick up a point of M, the tangent bundle of N is just, yeah, the X. You have to add, yeah, the tangent bundle of M plus the fibers, yeah. And then what I just did was creating a new submanifold which is ruled. So ruled means, yeah, this is clear from the context, that you have a foliation of the manifold, yeah, and each leaf goes by the capital F immersion, yeah, to an open subset of an affine subspace of the Euclidean ambient space. Yeah. Well, then you have the property that if you extend the original normal subbundle P to this new submanifold just by taking it constant, yeah, along the rulings, yeah. Well, it happens that delta is exactly the kernel, yeah, of the second fundamental form of the new immersion composed with the projection, yeah. So this construction is contained in this proposition, yeah. So with all the data discussed earlier, you have that capital F is a delta ruled extension of the original immersion, yeah, where D is the intersection between the ruling and the tangent bundle of M at point M. Moreover, there is orthogonal splitting of the normal bundle of the new immersion, yeah, where delta is just the kernel of the second fundamental form projected to one of these normal subbundle, and this subbundle is constant along delta. Let me mention that there are two extreme cases to be considered. Yeah. Well, one is that you started with a submanifold that already was ruled, yeah, having all these properties, so the extension is trivial. You get the original submanifold. And the other situation is, in fact, when delta is the relative nullity foliation of F. The relative nullity foliation is just the integral leaves of the kernel of the second fundamental form. I would like to say that, as my colleague Lucio Rodriguez said once in each talk, you have to sell one idea. Yeah. So in this commercial today, what I want to sell you is the idea of those rules and manifolds, right? You see, in some manifold theory, some manifold theory in some sense was started by Elie Cartan in the beginning of the last century. He did an incredible job. Yeah? And then it was dormant for a long time until in the 50s. Chern and Kuiper, yeah, somehow revived the subject and introduced the fundamental idea of relative nullity. Yeah? So you look at the kernel of the second fundamental form, yeah, and on any open subset where this distribution has constant dimension, this distribution is integrable, and the leaves are totally geodesic in the ambient space, in the manifold also, so there are Euclidean spaces in the case of the Euclidean space. And if the manifold is complete, this foliation is complete, and that's the way you get cylinders theorem and things like that. Yeah? So that was a fundamental idea. Yeah? So what I somehow want to claim that the idea of studying these rules are manifold, yeah, is like an extension of studying some manifold. I mean, the relative null distribution of some manifold. Yeah. So in this talk, I will try to show that this idea has some fundamentals, but I would like to mention, yeah, that those manifolds are basically not new. Yeah? There is the work I did a few years ago with Luis Florid, yeah, so which in fact is contained here, 2004. Yeah? So what we did was studying what we call genuine deformation of some manifold. Yeah? So let's see. You have a manifold and two isometric, non-congruent isometric immersion, yeah, in Euclidean space. You take any submanifold here, any, M, yeah, and you compose, so you have two immersion, yeah. So those new immersion are at least generically not congruent. Yeah? So that if you want to study with some manifold in Euclidean space with codimension greater than 1 can be deformed, yeah, well, of course this will be an example, many examples. So but these examples are not the ones you want to consider. They are not genuine, yeah. So in our work, we try to give information about genuine deformation. Yeah? I should mention that these situations, yeah, also happens, yeah, with respect to the problem I'm discussing today, having immersion with non-parallel first normal bundle. Yeah? If you have such a submanifold, then any submanifold inside the submanifold, generally we have also non-parallel first normal bundle. Yeah? Okay, so that's what we were able to prove. If you take a genuine deformation, G of F, of course you have to bound the codimension, and then this limitation that the codimension of is not greater than 5. Yeah? And then what we concluded, that F and G must be mutually deruled as above. So this means that the manifolds, at least until codimension 5, yeah, which admits genuine deformations, yeah, are this class of rules are manifolds. Yeah. Well, I should also mention that in this paper we were able to give a sharp estimate of the dimension of the ruling. Oh, this is wrong. It's 2p here. Yeah, there's no q, 2p. Yeah, copy and paste. Yeah. So, and there is this L, which is, it's the dimension of some normal subband, which is naturally related to the rulings. Okay. So, having said that, let's go back to the result I want to present today. Yeah. So I start with a locally substantial isometric immersion. So locally substantial means that no open set. Yeah. You cannot reduce the codimension of the submanifold in an open subset. Yeah. So, and then we assume that the first normal spaces form a proper normal subbundle of rank P. Yeah, of course, I want that this subbundle, well, it cannot be parallel in the normal connection. Yeah? And of course, I'm assuming always that I'm working in low codimension. So I'm going to use what I just discussed. So I need a natural, adapted to the problem, orthogonal splitting of the normal bundle of the submanifold. So I will consider the first normal bundle and its orthogonal complement. Yeah? And I will define as before these tensors. Yeah? So this tensor, what is doing is taking vectors, yeah, in the orthogonal complement of the first normal bundle, yeah, and then taking the derivative now in the normal connection, yeah, and the projection of the first normal bundle. So if the first normal bundle is parallel, this is 0. Yeah? Yeah. So we say that if F has non-parallel first normal bundle, this is not 0. Yeah? So I will call S the dimension of the vector space, which is the image of this tensor. Yeah? Okay? Now I'm assuming, of course, it's not 0. So this small s is always different from 0, and of course I will work on each connected component of some open dense subset where this function is constant. Yeah? So this bunch of subspaces on each of those components is just a nice, smooth vector subbundle of the first normal bundle. Yeah? So that's the theorem we proved. Yeah? Yeah, I know, it looks horrible. Yeah? There are many things in that theorem. Yeah? For instance, going to the very end, yeah, it says that some dimension cannot happen. Yeah? So you see, we start with the locally substantial symmetric immersion, where S is constant, and notice that we are showing a bound of S. Yeah? In previous work, this bound was 3. Yeah? We are dividing the statement in 3 parts. Yeah? So the first case, consider the case when S is P. So it's my phi is my tensor was onto in that case. Yeah? And the second case go to the other extreme. Yeah? And then there are all these intermediate cases. Yeah? And if you are able to figure out anything else about what the statement is saying, yeah, congratulations. But in fact, it's saying something very simple. Yeah? It's just saying that the only submanifold which has this property, yeah, of having, yeah, a non-parallel first normal bundle under this condition, yeah, are the ruled ones I just discussed, or submanifold of those. Yeah? That's it. Yeah? Of course, there is additional information. Yeah? But the only thing I want you to take home from this commercial, yeah, is that this family of special rules and manifold, yeah, also are the ones who really, genuinely have the property, yeah, of not having a parallel first normal bundle, yeah, in, say, local dimension. Of course, I'm not going to torture you with anything related to the proof, yeah, which is just multilinear linear algebra, basically. I just want to mention, for those who know something about the theory of submanifold, that a key ingredient is the basic property of regular element of a bilinear form. It was one of the concept introduced by John Moore. John Moore was able to read Cartan's original work and was influenced by the later work, especially by Chern and so on. Yeah? So he also made major contributions to the field, especially the theory of flat bilinear form that we all used a lot. So this idea is the new idea which comes in, which allows to generalize previous result. I also want to mention that there exist examples of some manifold that show that the condition was in part 3a of the theorem. So what was part 3a of the theorem? Well, part 3 of the theorem was when you are not in the extremes, and the submanifold is honest rule one. So that's the most interesting case. So there are some estimates there, and what I want to tell you is that they are sharp. So we went to the case where S, that dimension, has the highest possible value in our theorem, which is 6. So this is contained in the dimensions here. So we prove that there are rules of manifold with 4-dimensional first normal bundle. So that's, okay, things are sharp. So the result cannot really be improved if you are constrained to the limitation of the dimensions in the assumption of the theorem. Just to illustrate how this theorem works in low codimension, consider the most trivial situation, where P is 1, so the codimension. So if the first normal bundle has dimension 1, and it's not parallel, then mu, which is the dimension of the relative nullity foliation, is n minus 1, which means that Mn is just flat, a piece of Euclidean manifold. So only flat manifolds can have this property. So you see this is extremely strong. So move to next case. Well, codimension 2. So S and K, which are, S you know what it is, K was another constant which is contained in the statement. Well, there are in principle 3 possibilities where one is ruled out by the conclusion at the end of the theorem. So you have 2 cases. Either the relative nullity is n minus 2, and S is the full normal bundle. So those are called submanifold of rank 2. And submanifold of rank 2 have been extremely studied. So there's a lot known about this kind of submanifold. And then there are the other case, which is just a composition. A composition of what? Of a hypersurface contained in a manifold of case 1, which of course was a flat one. So part E is the interesting one, part 2 is just the obvious situation of having composition. So I'm going to start with 3, don't worry. So in the case of 3, it's the same situation. There are in principle 6 possible combinations, but you only 4 are possible. And then again, either the relative nullity has codimension 3 and S is everything, or F is ruled, one of our honest examples, but there is no extension. And then there is the ones where you have extension, 3 or 4, which are not new ones. They are some manifold of the 2 previous cases. Thanks.